Good afternoon, everyone. My name is Jixi, a software engineer at ByteDance Limited, Beijing. Today, I feel so happy to introduce our work, Primus, a unified training system for large-scale deep learning recommendation models. This is joint work with Zhejiang University and Shanghai Jiao University. Primus is developed for training large-scale recommendation models. It has been used as the default batch training system since 2020. The models are trained for many popular apps, such as TikTok, CapCut, Douyin, and so on. ByteDance internal DLRM daily training jobs has grown tenfold in past 5 years. 12,000 DLRMs are trained every day. Daily training data per model increased from 20 terabytes to 160 terabytes. And the CPU virtual cores used rising from 1.5 million to 9 million. Now, we have more than 20 million of CPU virtual cores and 200,000 of GPUs and 7 exabytes of total training data for DLRM training, so that we are focusing among resources, data, and model performance challenges. We illustrated the first challenge of DLRM training across a hybrid resource environment. At ByteDance, our infrastructure spans multiple resource scaling systems, primarily Yang and Kubernetes, with a massive scale of over 20 million virtual cores in total. In order to provide as many resources as possible for training, DLRM training jobs are often co-located with latency-sensitive online services and large-scale clusters for batch processing. Besides, to improve cluster utilization rates and training throughput, we leverage elastic training, dynamically adapting resource requests based on system ability and model status. The horizontal pod autoscaler in Kubernetes often suffers from slow reaction time. It doesn't scale up training jobs quickly enough to match burst availability. The vertical pod autoscaler in Kubernetes helps automatically tune memory and CPU resources, but it is difficult to implement in legacy resource scaling systems such as Yang. What is worse, we need to implement the about-to strategies on different clusters and ensure consistent behavior. The second challenge is handle large-scale multi-resource source batch and stream training data, as model training needs large volume data. In industrial training workflows, pre-processing cost, reading efficiency, orchestration complexity, usability, and stability are all critical. Processing cost. Feature engineering usually use a lot of Spark jobs, merging multiple sources data, consume large computing resources. Reading efficiency issues. Training dataset has exploded from 20 terabytes to 160 terabytes per day, adding pressure on I/O and instance processing. Orchestration complexity. We deal with diverse storage formats like TensorFlow records, Iceberg, Hoodie, are all Hadoop-compatible storage layers. Usability and stability. We need one framework that supports both batch and streaming, which is still hard to get it right. The third challenge is that even with optimized infrastructure, we have observed model-specific issues that limited the effectiveness in real-world deployment. One key issue is catastrophic forgetting in recommendation models. As the model is continuously updated online, it is especially problematic when user population shifts over time. For example, as preference from one period of time may differ significantly from another, but the model heavily biased towards recent samples, discarding long-term generalizations. Another key issue is delayed conversion feedback in ads system. In many cases, whether a user actually converts depends on the advertiser's asynchronously or offline reporting. Once the delay reporting can lead to a label noise, where true positive are mistaken treated as negative. That harms model performances. The question is, how we can reuse the historical instance to mitigate the impact of delayed feedback. To meet the three challenges, we propose three key solutions. The first one is unified resource scheduling. We introduced a unified training resource component that increase CPU utilization from 50% to 80%, improve overall training efficiency in heterogeneous environment. The second one is unified data orchestration. We design and implement an advanced unified dataset that can generate both batch and stream training instances. Under large-scale data scenarios, it accelerates training task generation by up to 23 times. The last one is unified training paradigms. We developed the MTRM model, which enhances historical batch instance replay to effectively mitigate catastrophic forgetting and delayed feedback issues. In real online A/B testing, that leads to an advertising revenue lift of 0.4% to 2.4%. Here is a traditional workflow for DLRM model training inside ByteDance. From left to the right, deep learning algorithm engineers submit training data and resource definitions to a Primus API server. Then we create a Primus job, including master and executors. All the resources are scheduled upon a unified scheduling layer, support both Yang and Kubernetes inside ByteDance. Executors are grouped as CPU-only data executors and GPU-only training executors. Primus master can do the unified data orchestration with both batch resources, including HDFS, feature store, and streaming sources like Kafka. Feature store is a customized instance management product enhanced upon Iceberg. Training data are first split by task and subsequently delivered to the corresponding data executors. Data executors read the training samples with the task meta and send training samples to the remote training executors. The remote training executors run a model with unified training paradigms which can handle both offline and online data concurrently in one model. Primus unified resource scaling by standardizing Yang and Kubernetes semantics using job CRD, enable multi-cluster scheduling and seamless scaling. Its dynamic scaling manager combines horizontal and vertical strategies, adjusts executor counts and resource allocations based on the real-time metrics. Primus enables a shared and unified resource controller for managing training workloads across large-scale clusters. This design allowed Primus to reduce scheduling latency even in a cluster with over 1 million virtual cores, which significantly improving resource utilization and training throughput. In Primus, we solve the challenge of orchestrating mixed batch and stream data scattered across HDFS, Kafka, and feature store for large-scale deep learning training. We introduced a 3-tier data definition: dataset, data stream, and data source to organize and serve data chronologically. Our data task generation, short as DTGG, provides data task efficiently across sources using operators and caching mechanism to reduce overhead. To support production scale workloads, Primus employs a centralized data component with a data driver and executors. The driver generates and orchestrates tasks while executors run them and serve data in a standardized format. Dynamic sharding, shuffling, and load balancing ensure stable, high-throughput data delivery even with scaled streams. To effectively combine online stream data with offline batch data, leveraging the strengths of both online and offline training, we propose a unified training paradigms. We design a mixture training recognition model, MTRM. MTRM controls the linear sequence of batch and stream data through different computational graphs for training, as illustrated on the right side of this figure. What's more, we introduced a mixture data prioritization mechanism, which optimizes the logic for multi-source data retrieval and provides row-level priority control, as illustrated on the left side of this figure. MTRM addresses catastrophic forgetting and delayed feedback by combining a memory tower for long-term storage and adaptive power for recent trains. The model processes batch and stream data through didactic paths, with flexible architecture supporting extension to various neural network models. To further enhance robust, Primus introduced an adaptive data prioritization strategy that ensures stream data is processed first during peak loads. This design dynamically balances data timeliness and system stability, maintaining model effectiveness even under high-load environment. In unified resource evaluation, we first demonstrate the dynamic horizontal scaling, which consists of two key components. The first one, large-scale dynamic parallelism. We compared a baseline with 400 fixed data executors against our setup, where executors scaled from 0 to 400 every 10 seconds. As shown in the left figure, our training throughput raised to 210 millibatch per second, similar to the baseline 205 millibatch per second, and the right figure shows our AUC is about 0.4% higher, proving the scaling strategy boosts the training effectiveness. The next one is auto-tuned data executors and training executors ratio. We compared a baseline with 900 fixed number 8-core data executors, with our setup starting at 458 core data executors. Both of them had 8 training GPU executors. From the table, our total training time and AUC are the same with the baseline. But we end up using only 690 data executors, saving about 23.33% CPU cores. Importantly, the cluster ROI measured as training throughput per core increased from 30.26 to 35.44, representing a 7% improvement. Then, we demonstrate dynamic vertical scaling. Tests were 2 key scenarios. The first scenario is excessive CPU allocations. We simulate with the CPU scenarios. Both jobs start from 410 core data executors. Based on model, stick to fixed CPU cores, Primus scale down about 1,600 CPU cores. Each executor drops from 10 cores to 6 cores. The CPU utilization jumps from 50% to 80% with no harm to the throughput or AUC. The second scenario is insufficient memory scenario. Here, baseline and hours start with 496 parameter server executors. Each has 16 GB memory. Baseline hits auto memory errors and break the training process. Primus dynamically scale memory. We avoid auto memory issues by boosting total memory from 7,000 GB to 9,000 GB. Training start time reduced 6.5%. The AUC climbs from 0.62 to 0.78. In unified data evaluations, we analyze Primus data task generation and data loading. For the data task generation, we run the dataset on 8-core and 24 GB memory data driver. This workload is a 20 days production dataset from 2 data lake tables with over 56 million underlying files. One thread data task generation cuts the task generation time from 58 minutes to less than 3 minutes, got 23 times faster. 4-thread data task generation speed up further to 42 seconds. Then we test the data loading for streaming data. We compared Primus with Flink as the baseline for streaming data loading. Simulation a production scenario where 10 out of 40 executors are intentionally slowed down. Primus hit 3.97 GB per second, 1.25 times faster than baseline, and raised the CPU utilization from 37.6% to 62.7%. The reason is Flink's 2-layer task manager struggled with slow executors in rebalance mode. Primus uses equal executors without back pressure, enable more efficient resource utilization across heterogeneous hardware. In unified training evaluations, we mainly focus on MTRM, mixture training recognition models, which chose 4 production models for CVR and CTR estimations, covering diverse scenarios. Both baseline and experiment use 1-year historical data for pre-training. In online training stage, without MTRM, there are only 1 single tower model, consume only stream data. With MTRM, a memory tower learns from 24 hours delayed batch data, and an adapter tower updates via stream data, same as baseline structure. As shown in the table, MTRM improved AUC about 0.03% to 0.07% across models. MTRM yields up to a 2.43% increase in ads revenue per model. Let's move to the lessons we have learned during implementation Primus. On the road towards unified resource scheduling, In early stage, Primus adopt a hybrid young Kubernetes deployment, as Kubernetes has insufficient scaling throughput and missing GAN semantics. As Kubernetes matured, Primus evolved to hide the schedule difference and support dynamic scaling. Ensure user appearance no disturbing during migrations. To optimize data access, we moved from insufficient data pipeline implementation to an era with native API client design, reduce CPU usage about 40%, especially when integrating data lake type like Iceberg and Hoodie. Finally, we shift from separate to unified executors for batch and stream data and address stream delays during peak loads with a continuous priority data queue. In summary, we present the Primus, a tri-unified training framework for DLRM that can encompass 3 primary innovations. First, Primus provides a unified resource scaling abstraction across multiple resource scaling systems. Secondly, Primus introduced a 3-tier data definition that facilitates efficient offline and online training with a single framework. Third, Primus supports an offline and online mixture training paradigms, allowed for continuous ingestion of historical offline batch data during online model training. It is so important and resulting in a significant increasement in advertising revenue. Since 2020, Primus has been utilized for all ByteDance production DLRM training. We continue to enhance Primus to achieve better efficiency and effectiveness in DLRM training. Please contact us through the emails and QR code below. We are hiring now. Thank you for your listening. Questions are welcomed. Thank you.